Hello everyone. While continuing with transmission electron microscopy, in this week lectures, mostly focus will be on the diffraction in transmission electron microscopy. Put simply, diffraction contrast arises because the intensity of the diffracted beam is different in different region of the specimen. So why we are going to study diffraction? So main aim is to perform imaging using diffraction contrast. And how diffraction contrast help? This diffraction contrast arises because the intensity of the diffracted beams is different in different regions of the specimen. So this variation may arise because of changing diffractive condition or because of differences in specimen thickness, right? So this variation may arise because of changing diffracting conditions or differences in specimen thickness. So basically we can easily determine the thickness of a specimen using this methodology, right? So here we need to know how to use this information, that some spot patterns which are also the diffraction patterns, that what type of information this diffraction pattern contains. So it is this diffraction pattern give direct crystallographic information, and there are a lot of things which we can easily get from this diffraction patterns. So diffraction patterns obtained through TEM give a lot of information, such as information about specimen crystallinity, whether the material is crystalline or amorphous, as they have different properties, so it is very easily we can differentiate it. And if it is crystalline, then we can get the crystallographic orientation too. Crystallographic characteristics. Crystalline means either crystalline or amorphous. Crystallographic or characteristics such as lattice parameter, symmetry, and so on. It is also possible to say whether one crystal is monocrystalline, or we can also say about its grain morphology. So it gives information about grain morphology, also orientation of individual grain, and also phase, whether there are different phases present or not, and how they are oriented, that also we can get from this TM. So as we have seen XRD, so there are certain similarities between XRD and diffraction pattern considering TM. With similarities, there are also some differences. So because of the differences in electron X-rays, we see difference in TM and XRD, right? Electron have much shorter wavelength than X-rays. Electrons are scattered more strongly because they interact with both nucleus and electron of scattering atoms through Coulomb forces. Electron beam are easily directed because they are charged particles, right? They are easily directed because they are charged particles. So with electric field we can easily direct them wherever we want. So while considering this, so how the scattering from a how this electrons scatter from the plane of atoms. So let's consider two planes, two plane of atoms, and we will consider two wave fronts. Okay, one, let's say W1 is the incident wave front, and after diffraction the wave front is given by WD. W scattering from two planes of atom. Here W1 is the incident wavefront and WD is the diffracted wavefront. So this WD corresponds to diffracted beam, and that depend on whether atoms are scattering in phase or not, and that will be determined by the angle between the incident beam and the diffracted beam. So, and the condition for individual wave being in phase is called the Lauer conditions, right? The condition for individual waves being in phase are known as Lauer condition. So to simplify this diffraction scattering phenomena, we'll consider it in vector form. Let's say incident vector k1 and the diffracted vector kt, and the angle between this incident and diffracted is given by 2 theta, and this k, capital K, is a resultant wave vector. So if let's say we consider two wave vectors here, which is dividing this angle into equal parts, then each part we can represent by k by 2 from simple geometry. So this k vector is given by kd minus k1 vector from simple vector addition. We can write this. So this k is called change in k, small k, due to diffraction. And this beauty of this geometry is we can consider this analysis for any kind of diffracted wave vector, and this theta may not be depending on the Bragg angle. So we can write this k vector, we can correlate with wavelength as it is inversely proportional to wave vector. So this will tell us about the energy of electron. So if we consider this scattering process to be elastic, then the change in energy there will be no change in energy. And we can consider this as equality, like k1 vector is equal to kg vector, then we can say this process is elastic and the electron energy is unchanged. So from simple geometry we can write sine theta as the change in wave vector, net wave vector divided by 2 by our incident wave vector. So from this we can write the by the change in wave vector is related with the diffracting angle. So as this k are measured in inverse of wavelength, so this k and k I are referred to as reciprocal lattice vectors, as the wave vectors have dimension of inverse of nanometer. So it is very important to remember theta by 2. If we will see it any equation sine theta by 2 or sine theta by lambda, then this corresponding to just k by 2 vector, and we can say sine theta by lambda is related to change in wave vector. So when we extend this argument to interference, let's say we have two beams that are scattered from 2 points C and D. C and B. There are 2 points lying at two different planes and two wavefront. Incident wavefront W1 after diffraction there is a net change in path difference. You can see this path difference. So when we consider two beams that have been scattered from 2 points, the ray travel different distances, giving a path difference of AC plus CD, AC and CD. And this we can correlate with two slit experiment, Young's two slit experiment, where this P1, two planes P1 and P2, they are normal to the vectors CB, which has a length d. The distance traveled by ray R1 is larger than the ray distance traveled by this ray R2. So the difference, path difference, will be given by from geometry AC plus CD as 2D sine theta. And this is the basis for Bragg's law, right? This is scattering happening from a plane of atom. So from, let's say we'll consider scattering from a crystal. Then let's say consider this k vector sine theta b by lambda, where theta, so when this we consider this theta as theta b, which is called the Bragg angle. So in TEM, mostly at Bragg angle, the electron wave interfere constructively so the path difference, let's say we denote it as this path difference AC plus CD given as 2D sine theta, will denote it as n lambda. Then our equation, above equation, will become at Bragg angle 2D sine theta b will denote it as n lambda, and for n equals to 1, it looks like lambda by d, and 1 by d is basically the distance between C and B, which we will denote it as our change in the wave vector. So this one is already equal to lambda k, right? So we can then equate this two, and we can say, we can correlate the change in wave vector to the distance between the 2 points, or we can say in crystals it's the interplanar spacing. So we denote this as G, and we say G is the lattice vector in reciprocal space. And one thing to note here is whatever is happening is diffraction rather than reflection. And these reflections are happening at a very small angle. So here, while considering Bragg's law, scattering is considered at a glancing angle, where, so this is its limitation, where the beam exits the same surface as it enters. So it's not basically transmission. So there is a correlation between, so this angle, glancing angle, is in the order of milliradians, or this conversion to angle is given by 0.573, or we can approximate 10 rads to 0.5 degree. This is the glancing angle. Mostly it is less than a degree, one less than 1 degree, mostly this glancing angle value is. So it doesn't matter how the atoms are distributed. So when we consider scattering from a plane, when we consider scattering from a plane, then it doesn't matter how the atoms are distributed on the two planes. So any two points if we'll consider will have same path difference of about 2d sine theta. So if it is generalized to parallel of planes, the diffraction from a set of planes having their distance d so these planes are oriented under Bragg diffracting condition. So when there will be incident beam, there will be resultant diffraction spots and for each corresponding plane there will be a diffraction spot. There is an incident beam, let's say, which is not parallel to the plane. Then there will be a series of diffraction spots we will get. The Bragg reflection then will be perpendicular to the set of planes. So when we consider the Bragg angle, then the Bragg angle is not the scattering angle here, rather whatever angle they will be diffracting will be the semi angle. So when we consider N in Braggs law, what does that mean? So as we saw here, there are a number of Bragg reflection happening periodically spaced and corresponding to the diffraction vector. Let's say G, 2G, 3G, they all are vectors corresponding to reciprocal lattice space. So when we will consider the scattering from, let's say, 3 different planes, then we will going to get the same result too, as two different scattering from 2 different planes. So to summarize, so electron whichever diffracting from a set of planes having spacing d, such that both have constructive and destructive interference. So it is possible to consider that n in 2d sine theta these belong to set of planes. Here we will say electrons are diffracting from a set of planes with spacing d by n. Rather we say d. Okay, so this equation can be applied to planes that are occupied by different atoms too. So this formula is universal. So while considering this dynamical diffraction, so the beam which has been strongly Bragg diffracted once is necessarily in perfect Bragg orientation to the diffracted back into the direct beam by the same set of planes. So what is the use of when we will consider this diffraction spot, there will be Miller indices will be using. So what will be the use of those? Now when we are considering diffraction spot, so how we will going to associate a spot in the diffraction pattern with a specific diffracting plane. So this Miller indices will help us to identify that. So notation like this, UVW, this is called zone axis. It depicts, it is a direction which is common to all planes of the zones. So this UVW notation is perpendicular to HKL plane. So this will be denoted as incident beam direction, and this will give us the V zone law, which is given by HU plus KV plus LW equals to 0. This is called, in last class we have seen, V zone law. So if there are many planes close to Bragg orientation, there will be a lot of spot from different planes. So if you consider the practical aspect of diffraction pattern formation, so there are two complementary ways. One is practical aspect of diffraction pattern formation. One is selected area diffraction and another one is CB. So in SAD pattern, they are sharply focused spot patterns that we use to select reflections for all imaging modes. But here in CB diffraction patterns, they are arrays of disks. So here such sorts can be associated with G. So here G can be associated with each disk. First we'll consider this SADs, which is also called selected area diffraction pattern. So what is the need to select a specific area? So all foils are distorted to some extent so that diffraction conditions change as we move around this specimen, as we need to select area of constant orientation. So if we consider diffraction pattern, it's a specimen plane. So this one is the plane of objective lens. This is the back focal plane of objective lens. This is the image plane. So let's say this type of image is formed. So as we are discussing, we wish to determine the orientation relation between two different crystals. That can be done by selecting the interfacial region. So here two things can happen, like here let's say if from P1 point and from P point, if it is not intersecting, that is given by the formation of when there is a error in selecting area, if the beams do not travel at the same angle to the optic axis, so this difference is due to the spherical aberration in the objective lens. So here P, which is the diffraction spot position for a perfect lens, and here we'll say C, the spot position with some spherical aberration. So there will be some distortion we'll find at the image, both image plane. So from here we can say the diffraction spot in SID's pattern is formed at the back focal length. At back focal length of back focal plane of objective lens, so here SID method for selecting an area is to place one aperture in the first image plane below the objective lens. We are really selecting an area which is the area in an image, but we always refer back to the volume of the diffracting specimen. So when we are working at an image, the plane, we do not need to focus the condition lens. We generally weaken this lens to give more parallel illumination, so that all rays are focused at the same plane, that is at the back focal plane, and the spot in the diffraction position becomes sharper. So two things we have to remember here. One, in SAD pattern, in SAD we have to be at eucentric focus position with an image of area of interest focused on the screen, and second point to remember, to focus diffraction spots with intermediate lens. So it is very easy to say, like we can use a small aperture to select a small area, but the objective lens is not perfect. So the beams which are farther away from the optic axis bend more strongly as they pass through the objective lens. So for rays entering the objective at an angle beta to optic axis, it's the optic axis. So image formed at magnification m is translated to a distance rm, which is given by rm equals to mcs. So the area we select using SAT aperture correspond to areas here PP1, the object plane. Here the error increases at beta increases, the error increases, so that it's larger for a larger Bragg angle, or for large g, which is the reciprocal lattice vector which we have considered. And again, if the lens is not focused on the SAT plane, consider specimen plane, the incident beam, shifting the selected area y. Let's say this is 0, 0, 0 plane, and this is any HKL plane. The if the lens is not focused on the SAT plane, images associated with the different G's, the G vector will be shifted with respect to one another. So here D is the defocus, and the shift in the selected area is given by y, which is equals to D times beta. So another question can be asked, like if sad aperture is placed at the first image plane, how it can affect the diffraction spot which is formed above it. So the relation between sad pattern and images can be seen through multiple dark field images. So if the first form sad pattern is done in its usual way, then by increasing the strength of the intermediate lens, we can focus it below the back focal plane. So instead of a point, we see a disc. Okay, this is the back focal plane. So we can see a formation of disc which is occurring because a defocused beam is either convergent or divergent at the back focal plane. So an under-focused convergent beam is preferred. Here we prefer under-focused convergent beam as it is more parallel than an over-focused divergent beam. So to understand what is happening, first we reduce the magnification of specimen at back focal length to 0. So as we increase the strength of the intermediate lens, staying and if we are going to stay in diffraction mode, we increase the magnification of these images. So the images are not in focus, but this can be corrected by adjusting the strength of the objective lens. So we can see that each disc corresponds to a reflection in selected area diffraction pattern. So the reflection that are bright inside it corresponds to dark bright it corresponds to bright discs. The area was close to the bright condition for that reflection. So the uncertainty in area selected to form this selected area diffraction pattern is one of the reasons for which we move on to the next diffraction pattern, which is CB diffraction pattern, and that will also give us more information about crystallographic orientation of our specimen too. So one disadvantage we can say of SAD is uncertainty in area selected to form this pattern. So after considering like why diffraction occurs, so then we need to calculate the intensity. So ultimately we want to understand the images we see. So to do that, the images, the detail about the images can be determined by the intensity of electron beam or the beam or the and this intensity varies for different position in the image. So the motivation to calculate the intensity of diffracted beam is they will give us the understanding of contrast feature in TM image. Provide understanding of contrast features in TM images. So in TEM we do a repeated diffraction. In TEM, like repeated diffraction is repeated diffraction takes place, which is called dynamical diffraction. So when we consider a perfect crystal, so we divide the crystal into two halves, one above the other. So the upper half diffracts the direct beam, the lower half further diffracts the direct beam. So we call this as a rediffraction of the incident beam. So because of this dynamical diffraction, it is very difficult to use the intensity of spot in electron diffraction pattern, except under some special condition for structure determination. So the intensity of electron beam varies strongly as the thickness of the specimen changes. So how to measure this intensity? So what we are going to do, so inside a crystalline material, we will think it in terms of block waves, because only certain wave propagation vectors are allowed in infinite periodic structures. So what we see in diffraction pattern that relate directly to the beam, because the diffraction pattern, whether in the microscope or on a print outside the crystal, whatever we see, that is outside the crystal. So what we need to calculate here? We need to calculate the intensity of beam at the exit surface of the specimen. That is, if specimen is given thin specimen, then incident beam, see direct beam, diffracted beam minus C1 plus C1, direct beam at different diffracting planes. These GIs are diffracted beams from for each point P at the bottom surface of the specimen. That is, we consider the exit surface. So how intensity is related to the amplitude is proportional to the square of it. So the amplitude of electron beam is given as scattered from unit cell is given by cell equals to E 2 pi I k r by r k dot r, where the summation is over all atoms I in the unit cell, and here theta is the angle at which diffracted beam is traveling relative to incident beam. So here the outside term explains how the wave propagates, and here 1 by r term is present because we have a constant flux of electron traveling through an expanding spherical surface. So here theta is angle between diffracted beam and incident beam, and here the outside term explains because of constant flux of electron traveling through an expanding spherical surface. Here F theta is the atomic structure factor, and here K is the diffracted wave vector which I have seen. As we are summing over all the atom in unit cell, so we can again write this summation term as a cell equals to equal to pi I k dot r into f theta. To find the intensity at some point P, we then sum over all the unit cells in the specimen. So the amplitude in a diffracted beam is given as phi g pi ai by zeta g n e to the power minus 2 pi I k dot rn to the power 2 pi I dot r. So here Rn represent the position of each unit cell. So here zeta g has a unit of length. As we can see, this has to be dimensionless. So this has a dimension of position, so this has to dimension of length, so this has to be dimension of length, make it dimensionless. So this psi g is also called characteristic length. G is called characteristic length for diffraction vector g, and is given by pi vc cos theta b by lambda fg, where fg is the f theta for deflection g. So this psi g gives us an idea about how nearly all diffraction contrast phenomena happens. So this has a unit in nanometer scale, and it is also known as extinction distance. This psi g is a scalar vector, and it depends on lattice vector through Vc and atomic number through Fg and to energy through lambda. So this psi g depends on lattice parameter through Vc vector, depends on atomic number through Fg, and depends on energy through lambda. So the direct and diffracted beam are detected outside the crystal, and we see them on the viewing screen. So if we think of the wave function inside crystal as being sum of beams passing through the crystal, so the direct beam which has amplitude psi 0, and the diffracted beam given by psi g's. So each beam will have the phase factor. The total wave function is written in terms of psi 0 e to the power 2 pi I psi g1 e to the power 2 pi I chi g1 dot r plus g2 per 2 pi I chi g2 dot r, and so on. These wave vectors chi 0 and chi d, it is wave vector which in reciprocal space and dependent on the reciprocal points g1 g2s. So for solving this wave function, we have to consider one diffracted beam G. So we make a two beam approximation. Here one diffracted beam is G and another diffracted beam is O. So this two beam condition means the crystal is tilted so that there will be only one strong diffracted beam, so that there will be only one strong diffracted beam given by s equals to 0, and all other diffracted beams are weak diffracted beams are given by either s very greater or very small than 0. And this contribution is ignored in 5G. So if amplitude 5G changes by small increment as the beam passes through thin slice of material, let's say dz, so change in 5G will be written as pi I by psi g phi 0 e to the power 2 pi I chi 0 minus chi d dot r plus pi I psi 0 phi g dz, and d phi 0 is given as pi I by psi 0 phi 0 plus pi I psi g phi g e to the power 2 pi I chi d minus chi 0 dot r. So here chi 0 minus chi d is the change in wave vector as the phi g beam scatter into the phi 0 beam, and similarly other one chi d minus chi 0 is the change in wave vector as the phi 0 beam scatters into phi 0 beam. So this chi 0 minus chi d is proportional or identical to k 0 minus k d. So which can be seen as G plus E for perfect crystal. These are basically the scattering terms or, or the diffracted beam terms. So this chi 0 replacing this k, because these k's are defined inside a unit cell, but in vacuums this chi 0 can easily replace these k terms. So this s, which is called the excitation error, so here we can say this psi 0 as the characteristic length for forward scattering, that is the scattering from any beam into itself, and this psi g correspond to scattering through an angle corresponding to diffraction vector G. So this two equations are called coupled differential equation, and when they are solved, this phi 0 and phi g are dynamically coupled, and they mean dynamically coupled means that the amplitude and hence the intensity of direct and diffracted beams are constantly changing. That is, they are dynamic. So we can write this differential equation as d phi g by dz equals to pi I by psi g phi 0 e to the power 2 pi I sz plus pi I by psi 0 psi g, and the other one will become d phi 0 by dz pi I by psi 0 phi 0 plus pi I by psi g phi g e to the 2 pi I sz. So this pair of equations are called Howe-Whelan equation. So this helps in understanding the diffraction contrast in TM. So when we further simplify it by writing, let's say 2 pi I s dot r will write as 2 pi I sz. We can write this when s is parallel to r and also s is parallel to z and r is also parallel to z. So we can approximate this sg vector to sz. The fundamental idea here is that at any given position in specimen, the change in amplitude of both the direct beam and the diffracted beam they depend on the amplitude of both the beams. The fact that the part of changing phi 0 is due to the magnitude of phi 0 itself, they give rise to term forward scattering. They remember the origin of scattering. So the scattering from phi g to phi g is also forward scattering, and we can see here because it's also depend on phi 0, although it takes place in a different forward scattering. So the forward scattering does occur, but it doesn't change the direction of beam. However, it does have a characteristic length psi 0, and this length is another way of saying we have a refractive index effect for electrons. So this characteristic length psi 0 helps in understanding we have a refractive index effect for electron. So coming to Kikuchi diffraction. So the incoherently scattered divergent beams of electrons give rise to paired arrays of lines in uh, diffraction pattern, and they are known as Kikuchi pattern. So the reason why the Kikuchi pattern form is that if the specimen is thick enough, then it will generate a large number of scattered electrons which travel in all directions and mainly in forward direction, which shows that they have been incoherently scattered but not necessarily inelastically scattered, but some of them lose some energy. So they are sometimes referred even to as scattered electrons. So these electrons can then be Bragg diffracted by crystal planes. Then what we get is basically the geometry from which we are getting this Kikuchi pattern. So this is basic geometry of Kikuchi pattern. So it relates what happens in specimen and what we see in the diffraction pattern. The electron generated here they are scattered in, we can see they are scattered in all direction. So we say they are diverging from a point, even but they are basically scattered at different points for the specimen thickness. So some of these electrons will travel at an angle theta b to HKL plane, and then the Bragg diffracted. Then they are Bragg diffracted by the specific planes. Since the scattered electrons are traveling in all directions, the diffracted beam will lie on one of the two cones. So we see cones of diffracted electron rather than well-defined beams because there is a range of incident k vectors uh, because of this range of incident k vector rather than a single k vector, we are seeing these cones. So we construct the cones by considering all the vectors oriented at an angle theta b to HKL plane, and these are called coastal cones. And the cone angle 90 minus theta b, we consider this very small, that angle that we can consider semi angle. So there are a pair of coastal cones for two vectors plus minus g and for plus minus 2g, and so on for different planes. So in coastal cones, when we see these coastal cones, what we see is we see in diffraction pattern we see the intersection of two cones with the screen or the detector. So since the screen and detector is flat uh, and it is nearly normal to the incident beam, the coastal cones appear as parabolas if we consider regions close to optic axis, and this parabola appear as two parallel lines. And for any pair of Kikuchi lines, one line correspond to theta b and the other correspond to minus theta b, and one is the G Kikuchi line or other one is G bar Kikuchi line. And another thing to consider here is we can see the scattered beam which was initially closest to the optic axis, and therefore this is the optic axis, and therefore more intense is farther away from the axis after being Bragg diffracted. So this beam then gives excess line, and the other deficit line gives the deficit of the diffracted beams. So this excess line is called bright and the deficit line is called dark. So from Kikuchi line, what we can conclude is that the distance between a pair of Kikuchi line may change at larger specimen thickness due to dynamic scattering. So the thickness of material do play a great role here. The Kikuchi line can also be produced by backscattered electrons. In SEM, this pattern are termed as backscattered diffraction patterns. So they are regarded as curiosity until like it was shown that we can map out the texture of polycrystalline material using these patterns without even thinning down the sample. Then the holes lines are very closely related to Kikuchi lines, but they are a little bit complicated due to inclination of black plane to direct beam. But they are also very good at characterize one sample. In real space, the Kikuchi lines can they also termed as zone axis pattern. But the physical origin of this zone axis pattern are different, and they are not associated with incoherent, elastic or diffuse scattering. There are strong similarity between Kikuchi process and operation of a monochromator in optics. Both select and diffract a particular wavelength or frequency. Next, considering the questions, the fringe contrast depend upon the sample thickness. That is true. Fringe contrast do depend upon the sample thickness. As the thickness variation will give different contrast, and hence we can say how the uniformity is there over the sample. So it is true. Sample thickness if the sample specimen is what, like only spots will be seen in diffraction pattern. If the sample thickness is thinner, then only we will be able to see the diffraction pattern, and if it will be thicker, then we will see the Kikuchi pattern. Now only we just see like how Kikuchi pattern only is seen by the thickness, like if it will be thicker, then we will be able to see nicely this Kikuchi pattern. So the answer will be the specimen is thinner, then we will see the diffraction pattern, and it will be thick, then we can see the Kikuchi pattern. And convergent beam diffraction is also called uh, nano beam diffraction, because we see in convergent diffraction the whatever scale we see, that is in nanoscale. That's why it's sometimes referred to as nano beam diffraction. So moving on to the next question, degree of scattering in TEM is a function of what? So degree of scattering in TEM is a function, basically depends on how much atoms are there lying in the electron path. So it should be number and mass of the atom. It doesn't depend that much on the energy of the electron beam. So that's why the wavelength, we will not consider the wavelength of the electron beam. So the answer will be the number and mass of atoms that lie in the electron path. Mass thickness contrast arises due to incoherent scattering of electrons. Next question, correction of astigmatism in electromicroscope possible by insertion of what kind of aperture we are going to use? So it should be SAD aperture. So when we are going to correct the astigmatism, so selective area diffraction aperture help us to correct this, which compensates the non-circularity of the image. So we use this SAD aperture. So zone axis for 100 and 010 plane is so as we see the as it is asked for the zone axis, so it should be in family of plane of 100. So this 100, 010 and 001, they are basically the family of planes. So that's why here the answer will be 001. 010 is basically same as 01, so it won't be the answer. But 110, similarly, if it would have been asked zone axis for 110, then this family of plane we would have referred 110, 101 and 010. So zone axis for 100, 010 should be 001. So what is the purpose of objective lens and aperture? It is to basically focus the electron beam emitted from the sample. So basically SAD aperture is normally used to form the diffraction pattern in TM. That's why the answer will be selective area diffraction aperture. As we already see, like SAD aperture do play a great role in TEM. They control a lot of parameters there. Next question, like what is the camera constant? Camera constant is given by L lambda. So ultrasonic cutting is generally used for what kind of material? So as we are using a very hardcore technique, so it has to be ceramic. In ultrasonic cutting, it will destroy the biological sample and also degrade the metallic and polymeric samples. So that's why it is only used for the ceramic ones. technique is used to make the 3 mm copper disc. As we are making a disc, so it has to be obvious from the option itself. It has to be disc punching, and ultrasonic disc cutting will destroy the copper material, as we already see. The ultrasonic cutting is mostly used for ceramic ones, so it should not be used for copper. Which signal is used for compositional analysis in TM? It is for compositional analysis we always use the X-rays. So X-rays from the sample. So from the bright field image due to change in thickness of the sample, because of this fringe contrast, we will able to see the bright field image. So the answer should be fringes. So the next question, how the powder sample are prepared in TM. Here it is prepared by distributing it on a copper field. So as we have already seen, for the contrast mechanism in TM, for lattice fringes variation, a phase contrast, tells us a good information about this lattice fringes. So the phase contrast should be the answer for this. The kinematic condition in image formation is TM arises when S should be very greater than 0. So camera length is not a physical distance. True, it is not a physical distance, rather it's just Eversper links the reciprocal lattice to Bragg's law. It's true. Stereography position is a true projection. It is true. Stereography position is a true projection, so it has to be true. So this, to see the spot size of probe diameter, FWHM is used, so it is true again. FWHM is a full width at half maxima. The diffraction spots become disk in CBED, convergent beam electron diffraction. In selected area diffraction, it is seen as a spot. In Hauer-Wheeler equation, it is used to describe the variation of the amplitude of transmitted and diffracted wave as a function of specimen thickness in dynamic condition. So whatever equation in Hauer-Wheeler equation is seen, it is in dynamic condition, and TM also, all the conditions are in dynamic condition rather than the kinematic condition. So the answer will be this. If we tilt the sample by small angle, and we see Kikuchi lines move but the diffraction spots remains the same. Kikuchi lines are formed by elastic scattering of inelastically scattered electrons. The bent contour is produced due to variation in its basically deviation parameter. This is it for this week. So we will meet next week for our last class. Thank you.